So now that you know how a cell is maintaining its resting potential of negative inside and positive outside, and that there's changes in concentration gradient between sodium, potassium, calcium, and chloride, I'm only going to focus on sodium and potassium here. So the sodium-potassium ATP channel is working in the background and is exchanging 3 sodiums to go out and 2 potassiums to come into the cell. But also you should know that there's also a sodium gated channel. And so this is a gated sodium channel. And what we need to understand is the nerve is going to pick up signals from its environment. And one way it can do this is it can use a ligand, which is just a chemical that's going to then stick to a protein. And so here you can see this ligand. And a ligand can then either open or close the gate. Okay, so this is really important. So here we have a picture of our sodium gated channel. So this is our sodium gated channel. This is the top view. This is the side view of it. And this is a cartoon down on the bottom. And so if we start off by looking at the cartoon, just to orient you to how this thing works, you'll notice that on the bottom here we have this red circle. And the red circle just indicates like a stoplight. The gate is closed, ions are not going through. And these little orange dots are your sodium ions. And so if a ligand comes over here, this green dot, so let's say you get these ligands, and the green dot then moves in and binds to the receptor site on the protein, it's going to modify the shape through an allosteric modification. Okay, so this is an allosteric modification. So we have allosteric modulation or modification. All right, and then the gate opens, and so now it's green. So then inside the cell, so this is outside and this is inside, you get a rush of sodium coming in. They're just going in, okay? And so when the gate opens, sodium goes in, and when the gate's closed, sodium doesn't go in. So here's your picture of the actual protein, and something I want to just highlight is we talked about this maybe a week ago or so, but these are your alpha helices, and remember they're in the membrane, so this is the membrane here. And so the outside of the alpha helices are all nonpolar, and so that's why it's membrane bound, right? So it can be in the nonpolar section. Well, what's going to happen is when this ligand binds here somewhere to the active site, it's going to change the shape and then allow things to cross the membrane. So sodium is positively charged, so it can't go across the membrane because the membrane's nonpolar and sodium's polar. So it needs to go through this gate in order to get in. So this is different than the sodium-potassium pump, which is actively moving sodium out of the cell and potassium in. This then is a gate that opens to let all that sodium come back in. So you should you should have watched the 2 videos that are showing you how concentration gradients cause ions to move, and also how they can create an electrical gradient across the membrane. So I'm not going to talk about those 2 things in this video.